good morning. So today we'll continue coordination chemistry. It is the lecture number 10. So under that CFT in case of tetrahedral geometry. Okay. In previous classes you are well familiar the CFT with respect to octahedral with strong field as well as weak field splitting, and also you learned how to calculate CFSE, okay, in case of octahedral. Today we'll discuss the CFT, crystal field theory, with respect to tetrahedral geometry. So here coordination number is 4, means there are 4 ligands going to react with metal ion. Okay. Now in tetrahedral field, the 4 ligands are imagined to occupy the alternative corners of a regular cube. So this is a regular cube, and where the 4 ligands are occupying alternative corners. And now imagine the 3 axes, or the direction of 3 axes, they are pointing to the center of the opposite faces. That means the 3 axes are passing through the center of opposite faces in this way. It is shown in the figure. Okay. Now during the formation of a complex, the metal ion is going to react with 4 ligands. When the ligands are quite away from the metal ion, there is no interaction. So all the 5 d orbitals are in ground state and they are degenerate. So when the ligand field is approaching, or it is coming nearer to the metal ion, now imagine the metal ion is spherically surrounded by the symmetric field created by 4 ligands. So now all the 5 d orbitals are equal distance or equidistant from the ligand field. Hence there is an interaction, and as a result the energy of 5 d orbitals is raised, and it is raised with same extent. Therefore all the 5 d orbitals are still remain degenerate, and this is only a hypothetical state. Now imagine the surrounded ligand field is no more spherically surrounded. Now it is concentrated at particular positions with respect to metal ion. That means around the metal ion at a particular positions. They are concentrated at a particular positions with respect to metal ion in space. Okay, like this. So now say the direction of approach of ligand towards the metal ion is not exactly along any of the axes, even not exactly in between the axes. That means the direction of, or the path of direction of the approaching ligand is not exactly along any of the axes, or even not exactly between any of the axes. And you are well familiar the orientation of 5 d orbitals. These 2 are lying along the axis, and these 3 are lying in between the axis. That means these 2 are oriented along the axis and these 3 are oriented between the axis. Now in this case, in case of tetrahedral geometry, say none of the d orbitals are lying exactly on the path of approach of ligand, and thereby there is no head-on interaction, but the position of these 3 orbitals, the orientation of say dxy, dyz, dzx orbitals, they are nearer to the approach of ligand. That means direction of approach of ligand. Hence they experience little greater forces of repulsion than these 2 orbitals which are lying quite away from the direction of approach of ligand, from the direction or the path of the approach of ligand. Thereby these 2 orbitals experience lesser repulsion, and these 3 orbitals which are nearer to, not exactly on the way, they are nearer to the direction of approach of ligand. Hence out of 5 d orbitals, these 3 are raised by plus 4 dq energy, and these two are lowered by minus dq energy, and they are named as e orbitals. These two orbitals are named as e orbital, and these three orbitals are named as t2 orbitals. And this is exactly opposite that happened in case of octahedral. So octahedral, it is reverse. So three of them are lowered, two of them are raised. These two are raised and these three orbitals are lowered in case of octahedral. But now this is exactly opposite to that happened in octahedral. Okay. So now this picture indicates the splitting of d orbitals in tetrahedral geometries. So now any electron, if it enters the lower energy level, it stabilizes the system. That means it stabilizes the complex by minus 6 dq energy. And those entering T2 orbitals, that is higher energy orbitals, they destabilize the complex or the system by plus 4 dq energy. Okay. So now in this case, see the splitting energy, that means crystal field splitting energy, it is shown by delta T. T stands for tetrahedral geometry. Okay. So now delta T is always less than P. So in case of tetrahedral, delta T is always less than P, because delta T, it is the crystal field stabilization energy, splitting energy, which is due to the interacting with only 4 ligands. Okay, therefore delta T is quite smaller and P is always greater. So okay, now with this knowledge we'll move on to the next, that is calculation of crystal field stabilization energy. So in case of tetrahedral complexes. So in case of octahedral, okay, octahedral, you have seen there is a strong field as well as weak field ligands. Okay, and now the strong field ligands, okay, where this delta O, so delta O is greater than P, where delta O is greater than P, and thereby what happens, say instead of going to higher energy level, they started pairing at the lower orbital first. Therefore these are the low spin complexes. These are the low spin complexes. But in case of weak field, delta O is lesser than P, and therefore the resulting complexes are high spin complexes. They are high spin complexes. But in case of tetrahedral, okay, so here delta O, it is always less than P. Delta O is always less than P. Therefore, here the resulting complexes are always high spin complexes. They are always high spin complexes. Okay. So now with this, we'll move on to the calculation of crystal field stabilization energy. Crystal field stabilization energy. Okay. So now for dx system, the electronic configuration is e raised to p t2 raised to q. Okay, because e orbitals are filled first and then it goes to higher levels. Okay, and now x is equal to p plus q and CFSE is, say, minus dq minus 6 dq into p plus 4 dq into q. Okay, plus m number of p. So now we'll calculate by taking different dx systems. So if dx is 1, the electron goes to lower energy level first according to Aufbau principle. Therefore E1. So energy is decreased by minus 6 dq. Therefore CFSE with this formula, it is minus 6 dq is the energy. Okay. When there are 2 electrons in d orbital, the second electron is also goes to lower energy level. So d1, and in the second orbital d2, second electron will enter, and thereby minus 12. So minus 12 is the energy, that is crystal field stabilization energy. Now D3 system. Now in the D3 system, the third electron, it goes to higher energy level, because here delta T is lesser than P. So pairing is difficult. Lesser than P, pairing is difficult. Therefore, it goes to higher energy level, that is T2 raised to 1. So now the energy is raised by 4 dq than this. Therefore here it is 12 minus 4 gives you minus 8 dq. So with D4 system, once again the electrons are, this is singly occupied and this distance is lesser, easily it goes to higher energy level. Therefore the next electron, the fourth electron, enters T2 orbital. So thereby once again plus 4 dq, it comes to minus 4 dq. Okay. Now if you imagine the D5 system, so E2 to D5, suppose there are 5 electrons in d orbital, 1 2 3 4 5. So thereby here it is 2 electrons here, 3 electrons here, all are unpaired. Okay, all are unpaired, singly occupied. All the 5 d orbitals are singly occupied. Pairing is difficult, therefore it doesn't pair up here. The third electron goes to here, similarly fourth electron and fifth electron. So now energy is equal and opposite. So 2 electrons here means minus 12, 3 electrons here means plus 12 dq, totally 0 dq. Okay. So now with this, we'll go for the next system, that is say d6 electrons. So d6 electrons, now the electron has to enter the lower energy level. Now it is E3 and T2 3. So 3 electrons here, that means minus 6 is decreased, and in the last case it was 0, and next the electron enters the lower energy and thereby it decreases by minus 6 dq plus 1 pair of electron. Okay. So similarly D7, it also enters the lower energy, T2 3, and it is minus 12 dq. Is it? 2 are paired, that means 4 electrons are paired. Now D8 system, E4 T2. Now it goes to higher energy level. Now here it is 4. So now the energy is increased by plus 6. Okay, therefore add plus 6 to here. It is minus 6 dq. Not plus 6, plus 4. Add plus 4 to this one. So it is minus 8 dq plus 3 pair. Okay. So D9 system, it is completely filled and the next it goes to 5. So plus 4, it is minus 4 dq plus 4 pair. Okay. And D10, in all the case it is same, D4, T2, 6, and it is 0 plus 5 pair. Okay. So this will be the answer. So now with this, we'll move on to the next class. Okay. Thank you.